Okay, so I'll get straight into it. So we've been through 2 days. We've invested quite a lot. Yesterday was a little bit more interesting. So we got to see how the material on Tuesday gets applied in various architectures. And today I want to take that a little bit further and talk about the CRAM cognitive architecture. It is still an overview. So my goal is to explain the rationale for its design, the design principles. I'll take you through the structure, and then we'll have a walkthrough of how it operates, how it executes tasks and achieves goals. So that's what we'll do. I'll finish off then with a little bit of just a few words on the implementation side of things, revealing what actually goes into making a system of this complexity possible in terms of the software engineering, but I won't spend a great deal about it, talking about that. But there's plenty more of material. I'll just remark here straight away that the lecture class we're doing today really it's on the website, cognitiverobotics.net, and it's effectively a concatenation of lecture 1 and lecture 2 in module 7. And as you can see, if you want more details on how to program and use CRAM, there's more material here. And it's continually being updated. I'll be refining and adding this as I learn more and more, as I get more practice, and as I borrow material that's continually being developed by the team. But for the moment, it's a fairly mature snapshot. Okay, so let's get straight into this. So to begin with, CRAM stands for something. It's an acronym. So it stands for Cognitive Robot Abstract Machine. And we'll see as I go through this, the word abstract has a very, very special meaning. It plays an important role in the foundations and the design and the implementation of CRAM. It's a hybrid cognitive architecture. We know what that means now. Hybrid with a little h in the sense that it combines symbolic and sub-symbolic representations and processes. And it does so in an extremely elegant way. And I'll show you how that's accomplished when we talk about a construct or a mechanism in CRAM in a subsystem called NOROB. And I'll talk in particular about accessing what are called episodic or narrative-enabled episodic memory. So we'll get to that. So I'm just flagging this here so that you'll recognize it when I get to it, this integration of symbolic and sub-symbolic. So this idea of this hybridization is taken very seriously in CRAM. So it was introduced by Michael Bates in 2010. I wasn't sure what verb to use here for introduced. I settled on introduced because that's when effectively it was revealed to the world. But like all overnight successes and things like this, it has a long history preceding it. At least 15 years of work went into getting to 2010. And we're now 10 years on from that. So it's been developed significantly since 2010, based on several research projects over the years. And it continues to mature. And I'll tell you about one of the major research projects that are now ongoing, which is providing the vehicle for developing CRAM even further. It has a very specific focus. The focus of CRAM is robot manipulation, and in particular, robot manipulation in everyday activities. So the type of tasks that people carry out in their households, in kitchens, or perhaps in a shop, the type of things that we're normally used to doing. And that's important because it means that it's targeting the integration of robotics into the domestic world. I'm going to begin by showing you a short video. We mentioned yesterday the idea of benchmarking, and I mentioned the fact that CRAM adopts this as a working methodology. So every year we've got these marathons, these demonstrators, which identify or show the capability of CRAM at a particular point in time. They're like snapshots in the development of CRAM. It's actual practical capabilities. So this is a short video. It's narrated by Gayan Kazayan, and she'll walk you through a demonstration of what CRAM is capable of doing today. So let's get started with this.
Hi, my name is Gaia and I'm a PhD student at the Institute for AI at the University of Bremen. In this video, the PR2 is performing the household marathon demo of the EASE project. The idea of the demo is that the robot executes different variations of mobile pick and place, whereby it needs to act completely autonomously with the minimal amount of human interference. The first task is to set a table for cereal breakfast for one person. This involves 5 objects: a bowl, a spoon, a cup, some milk and a box of cereal, which have to be brought to the dining table. Afterwards, the table has to be cleaned up, so the washable objects are placed into the dishwasher, the cereal box is placed back into its storage location, and the milk box is thrown away into the trash, as it's assumed to be empty then. The perception system that we use is called RoboSherlock. It employs an ensemble of experts approach based on the principle of unstructured information management. Importantly, it works in assumption-free scenes, which means, for example, that we don't expect a supporting plane to exist for each object. This is required, for example, for the objects in the dishwasher or in the door of the fridge. The motion control framework that we use is called GISCARD. It does whole body control. For the PR2, this means that we control the arms, the torso, the base, and the head simultaneously. It uses a constraint and optimization-based approach with which we can define multiple goals at the same time. For example, grasp the object while looking at your hand, staying away from the joint limits, and avoiding collisions with the environment. The plan executive that we use is called CRAM. It uses the reactive planning approach, such that the plans concurrently perform the motions and monitor their execution. Simply put, this means that if a failure happens, such as an object slips from the gripper, the robot reacts immediately. The sequence of actions and the failure handling strategies are engineered according to a general model of mobile pick and place, and the parameters of actions are inferred at runtime by querying the knowledge base. There are a lot of challenges that need to be solved in order to master these mobile pick and place actions. First, the robot needs to have an enormous amount of knowledge about its environment, the task, its own capabilities, the user preferences, the physics of the world, and common sense rules. Second, the robot needs to be able to execute its actions in a wide range of variations. For table setting, this means that it should be able to get any object from any location in the environment and place it at any other plausible location. The robot also has to deal with the non-determinism and the partial observability of the world, which simply put means that acting in the real world very often leads to failures, and the robot needs to be able to recover from them. And it needs to keep its beliefs about the world in a consistent state, as close to the state of the real world as possible. Finally, in order to reach human-level skill and mastery, the robot needs to be able to improve its performance over time based on collected experience. For more information, please follow the links in the description below.
Okay, so that's what CRAM can do. And my goal over the next hour or so, perhaps a little bit longer, is to explain to you how CRAM makes that possible. So let me start with some design principles. So the first key thing to understand is that CRAM is built around this idea of an end-to-end manipulation. And that means that we start with a vaguely stated high-level goal, and we try to map that into specific low-level motions, the motions that are required in order to actually accomplish that goal. So we've got explicitly represented knowledge and behavior descriptions, and we have prospection and memory mechanisms, which are based on an inner world model. So that's what's doing the internal simulation. Now, the goal is to map from the vaguely stated goal, a high-level goal, to the low-level motion plan, and that's accomplished using what's referred to as a generative model. Now, there's a technical understanding of a generative model, and I'll get to that later on. For the moment, I just want to treat it as a way of tightly coupling symbolic and sub-symbolic knowledge representations it's working on and the environment in which it's working. Effectively, this mapping, the generative model is a way of modeling how the outcome of an action is related to the action itself, so that if you can identify what the outcomes you want, then you can infer what are the motions that are necessary in order to accomplish that. So that's the idea of the generative model. So these vaguely stated high-level goals, then, they can be requested by another agent, or they can be self-generated. It's important in the end-to-end idea that when you do the mapping, that if you have constraints and you know them at this high level, then you can propagate them down to the lower level when you're mapping from the high level action specification to the low level motion plan. And the key thing here is that we're also going to evaluate whether or not the goal was accomplished well or not in the same space in which you formulated, and that's the observation space. So this is different in a number of architectures and approaches. We would evaluate the success or failure of a symbolic plan at a symbolic level. That's not the CRAM approach. The CRAM approach is to look and see whether or not you were successful in accomplishing the goal or the action in the visual space, in the perception space. And that's exactly the same space in which you imagine, as we were talking about yesterday and the day before, and you imagine what it is you want to accomplish. CRAM focuses on an abstract specification of robot actions. And yeah, by abstract, I mean that we specify them in an underdetermined, in a sort of a vague way. So the action specifications are framed in terms where you do not have all the knowledge which is required to accomplish the action. So you might say, fetch the milk and pour it in the bowl. Or you might say, fetch the spoon. Well, where is the milk and where is the bowl and how should I put it into the bowl? And all of that knowledge has to be provided and made available to the robot so that it can do this mapping from the high level underdetermined action description to the low level motions. We refer to that as being to resolve at runtime these requirements for knowledge while the plan is being executed. And it's done and it's accomplished by querying in real time a knowledge base. It's a multi-knowledge element knowledge base, and it's called NOROB. I'll show you about that later on. But there is prior knowledge which is embedded in it. There's also knowledge about the current world states. And of course, then there's also knowledge about the robot's current sensory motor state. So all of this knowledge is encapsulated and made available to the plan executive as it's carrying out the plan, which is going to fetch the milk and pour it into the bowl. So this control program is stated in what's referred to as a generalized action plan. So we have one plan for each category of underdetermined action description. So we have a generalized action plan for fetching, for placing, for pouring, for cutting, and as we'll see shortly, we have a generalized action plan for fetch and place as well. Most roboticists are familiar with the term pick and place, and I'll be speaking mainly about fetch and place. The difference between fetch and place and pick and place is that with pick and place robot applications, typically the robot is where it needs to be doing the picking and the placing. With fetch and place, you don't make that assumption, which means you have to go somewhere appropriate in order to be able to pick it up. So there's an additional degree of freedom involved in the fetching. So then the plan can be executed, and the plan can also be reasoned about. So this is very important in CRAM, as we'll see later on when I talk about metacognition. So in robotics, we execute plans in order to act in the world and accomplish tasks. But because of the way that the plan is formulated in CRAM, specifically it's formulated as a first-class object in a predicate logic and a first order logic, it means that the plan itself can be viewed as data. It's both program and data, and therefore it can be reasoned about. And therefore it can be transformed, and that means it can be improved. And so you get this element of self-programming in the design of CRAM. The idea that the CRAM program or plan executive can reason about its plans and improve them. And therefore CRAM itself can improve. If you want to call that development, you can. So now we have this mapping from a generalized action plan to a motion plan. So the generalized action plan is the key concept in CRAM. And then the motion plan, the thing you're mapping this into, these are made up of primitive motions, and each of these primitive motions have parameters associated with them to define exactly what that motion is. And the goal of this mapping is to find out what are the parameter values that will make this action successful. So how do you do the mapping? Well, the mapping happens in a three-step refinement process, and we call this contextualization. It's contextualization actually is a very appropriate word because it means using information or knowledge of your current context in order to reduce the ambiguity which is inherent in the vague statement so that you can satisfy the requirement for knowledge and identify the knowledge that's needed to accomplish the action given the current context. So what we're after is we want to identify the values of the parameters of the motion plan which maximize the likelihood that these body motions will successfully accomplish the desired action. So if you can just digest that for a second, because this is actually crucial. CRAM is all about taking a statement, a description saying, get me a glass of milk. And then CRAM says, okay, well, what do I need to do in order to satisfy that requirement? And to be sure, or as sure as possible, that when I carry these actions out, and these actions will comprise these elementary motions, to ensure that I'll be successful in accomplishing or achieving that goal. So throughout this, we're going to use three sets of terminology. I started off by telling you about an underdetermined action description. That's like a natural language statement. Please get me something. But then in terms of executing it, we talk about a generalized action plan. And that's the core of the CRAM approach, this idea. And I'll show you an example of that in a moment. Within that plan, we have an entity called an action designator, or a high-level action designator. And this designator is the crucial component of this generalized action plan. And I'll explain it by example in a moment, but let me just say here that this designator is a way of saying, I know I need to know this, I don't know it yet, and I'll find it out when I'm executing the plan. So think of designators as being placeholders for required information. And they're the key elements of this generalized action plan. To explain that a little bit further, I wanted to refer you to a well-known paper by Randall Flanagan and Miles Bowman and Roland Johansson, published in 2006. And I want to show you this for two reasons. In the last couple of days, we've been making a big play about the importance of prospection in cognition. And so when I pulled up this paper this morning to put it into this presentation, I was delighted to see this statement in the second half of the abstract, which says that successful manipulation requires the ability both to predict the motor commands required to grasp, which is exactly what CRAM is doing. It's predicting what motor commands do I need in order to do this manipulation successfully. And CRAM operates by doing this prediction. And then to predict the sensory events that arise as a consequence of those commands. So this is the generative model. So effectively, if I was to do this, this would be the sensory motor consequence of doing it. And that's what's captured then in the generative model. And this is the way that CRAM implements that. So the top half of this diagram here is effectively a schematic which is taken almost directly and just recast from the Flanagan paper. So the idea is that we've got elementary motions, they're called sub-action controllers here, reach, lift, transport, release. And each of these has a task sub-goal. The hands are in contact with the object when you're reaching. Then you lift, the object is lifted off. Then you transport it, well, it makes contact with the surface to which you're transporting, and then you release. And then the object is that the hands release it and you're no longer in contact with the object. CRAM decomposes that just a little bit. So we talk about these motion phases in CRAM. And then these are our motion designators: reaching, grasping, gripping, lifting, going, reaching, putting, releasing. So it's a slightly finer grained decomposition, but it's identical in the approach and in the philosophy to the approach proposed by Flanagan et al. What's crucial here is to notice that each of these motion designators has a set of motion parameters associated with them. Now, the motion parameters are important because they tell you what information is required, but it's the value associated with the parameters that makes all the difference. Depending on what pose you put in here will determine where you reach for. Depending on what value you put in here will tell you what your gripping force is. And of course, that's going to be dependent on the object that you're gripping and its weight, for example, and its softness or flexibility. So what we need to do effective manipulation in robotics is to know or to predict what are the appropriate values for these parameters of these elemental motions, which together make up the action. And you can concatenate actions together to carry out tasks. So this is the framework in which I want you to understand CRAM. CRAM is a cognitive architecture which is totally focused on providing the appropriate values here for these motion parameters, such that it maximizes the likelihood that when you carry this motion out, it will successfully accomplish the action that's been requested. Okay, so how does it do it? Well, I'm going to do this in 2 steps. I'm going to first of all take you on a quick tour through the structure of CRAM in the same way that I did with SOAR and specifically with Isaac, and then Isaac I walked you through a schematic of how it would carry out an action. So I'm going to do exactly the same thing here. There are 5 core elements in CRAM. The first one is the CRAM plan language executive, and CPL, the CRAM plan language. It is a language, and it is a language in which we write plans, the programs which make CRAM work. The second one is NOROB. It's in version 2. After about 2018, it was updated. And so I'll just speak of it, NOROB, generically. So it's a collection of knowledge bases and associated reasoning processes. And I'll take you through that in detail in a moment. We've got Robo-Sherlock, which you heard Guyan mention. That's the perception executive. We've got Giscard, which is the action executive. And then finally, the 5th element is a metacognition system called Cogito. So let me walk you through each of these in turn. So I'm going to refer to the CRAM plan as the plan executive, just for short. So tasks are accomplished by executing plans written in CPL. And CPL is an extension of Lisp. So a CPL plan, because of that, then represents all of the aspects of the plan effectively as first-class objects in a first-order logic by virtue of the fact that CPL is an extension of Lisp, which means that the plans can be executed, of course, or I'll speak about interpreting them. But of course, the plans, because they are first-class objects in a first-order logic system, they can also be the subject of reasoning, even at runtime. And that's particularly relevant when it comes to the metacognition system, Cogito. So that the plans, which are the programs which make the system work, are also the subject of introspections, and they can be adapted and modified and enhanced. So the plans specify how the robot should respond to sensory events in the world around it, changes in the robot's belief states, and very, very importantly, failure. Anyone who has done any practical robotics knows that failure just comes with the territory. You have to be prepared to fail. Things don't go according to plan. It makes sense when you say it that way. And so building in failure handling and acting accordingly when failures happen in an appropriate way is a very, very important part of the overall CPL plan language approach. I won't say much about the details of programming CRAM this afternoon, and I certainly won't say too much about the amount of additional plan coding you have to put in order to handle these failures. But anyone who's ever done any software engineering knows, yeah, you normally spend 2/3 of your functional code handling or catching and dealing with exceptions, as opposed to the functionality associated with requirements. And my experience of my limited experience of programming CRAM bears that out exactly. But that's just the way writing code is, and there's no simple way around that. So all of these things then can be queried, inspected, and reasoned about because the CRAM plan language is an extension of Lisp. So a plan then, as I said, comprises these things called abstract plan designators. And as I said, they are effectively placeholders. So they require runtime resolution. In other words, they're part of the plan, but they don't yet provide the information you need. And so you have to resolve those designators when you execute the plan. And you do that at runtime, and you do it, and you make use of the fact that the current context when you're carrying that out. There are 4 different types of plan designator. There are action designators, object designators, location designators, and motion designators. So the actions describe the actions that you want to carry out. Object designators are placeholders for information about the objects that you're going to manipulate, their pose, their appearance, their potential grasp points. Location designator identify places you should be if you want to be doing things successfully. And it's important that location designators are not just single-valued singletons in the sense that they give you one value, that they can give you a distribution of possible values that you can choose from. And then finally, the lowest level of all are the motion designators, and these correspond to the elementary movements, these elementary motions that I showed you in the diagram, where I showed you how CRAM implements the Flanagan model of action execution. So the plan executive interprets these generalized action plans, and they're written in Lisp. And they look like this. Now, if you haven't been programming in Lisp for a while or never have, it's a slightly different way of thinking about it. It's a functional programming language, and it's extremely powerful. But some people find it off-putting because it's not an imperative language, and it doesn't have that look and feel that we're used to when we're taught imperative programming. But nonetheless, once you get used to it, it becomes a way of thinking. And it's a very, very, very powerful way of thinking. So without going through the details of this plan here, but this is a fetch and place generalized action plan. And there are 2 actions within it. It says, please perform an action. Now this here, say this is your action designator. So perform an action of what type? Of type fetching, and then perform an action of type placing. So that's why it's a generalized action plan for fetch and place. There's some additional things here that we need to know. There's this construct here with robot at location, and that effectively says you better be at the right location when you're going to do the fetching. And so there's a question mark in front of this. So this is going to be identified by querying the knowledge base. And also when you're going to put it down and place it, you need to find the location that you should be, or a set of possible potential locations, which would be a feasible place to deposit the object. So this is the idea. So that action plan then gets extended. So we have here my action of type fetch and place is now being expanded, and it says, okay, for what am I going to fetch? I have to fetch an object. So here I have an object designator. It's an object of type cup, and I'm going to put it somewhere, so I need a destination. And so the destination here, I've got my location designator, and it's going to have to provide information at runtime. And here, well, a location, but where? Well, it's a location where I can put something on what? On a table. So this is an example of how a CRAM plan appears. This is what you program. This is a generalized action plan. And these designators identify the information that has to be resolved, provided at runtime in order to accomplish the task. Which brings me into all of the other elements or components of the CRAM cognitive architecture. So the plan executive, which needs to resolve these designators in order to carry out the plan, accomplishes that by querying a priori knowledge, which you can embed in the plan itself and in the tutorials that I've been doing, and that's where we put it. We encode them as fact sets in the plan itself. But more powerfully, we use the no-ROB knowledge base, and I'll tell you a little about that in just a second. But of course, you can also query the perception executive. So in other words, the plan executive has access to all the knowledge it needs over here, and it also has access to the current context and what the robot can see using the perception executive. And again, I emphasize the whole point of this is to try and identify the values of the motion parameters into which the generalized action plan is going to be expanded. It's going to be expanded into this motion plan. These motion plans have parameters, and those parameters need values. And the idea is to identify the values of those motion parameters such that the likelihood of succeeding in carrying out that action is maximized. Speaking a little bit more about designators, let me show you, just for relief, another presentation by Gayan Kasayan, specifically about designators. So this is just showing you different types of designators and then how CRAM resolves them. So here we have a designator picking it for picking. This time it's picking up a knife. And if you look over here, you'll see Robot Sherlock has identified a knife. That's on the right-hand side at the top, and that allows it. So that information then is the information which is effectively provided by NoRob or Robot Sherlock at runtime in order to resolve that designator. Another one picking up a bottle. Gayan mentioned in the opening video that Robot Sherlock is quite powerful in that it doesn't necessarily assume that there's a supporting surface for the objects when it's doing its computer vision. And you'll see an example of that coming up in just a moment. In other words, here everything is just sitting on the table, so there's a supporting plane. And we know that that can make computer vision a lot easier. Not easy, easier. Computer vision is never easy. So now here we go. So here we have an object which isn't being supported by some ground plane. Okay, so these were just some examples to give you a feeling for what action designators are and how they are resolved at runtime. Again, the idea, an action designator is going to be expanded into a motion plan, and those motion plans have parameters, and you need to provide the values in order to make the action successful.
David.
Okay, which brings me conveniently to NoRob. So NoRob is knowledge representation and reasoning executive in CRAM. And it uses this concept of a generative model to identify the motions that are most likely to succeed when you're executing your action. In particular, it's not just the motions, because the motions are going to be given by the plan executive in the way that it knows how to expand its general action plan into the primitive motions, but what it needs in particular are the parameter values for these elementary motions. And so you can think now in a more technical way of a generative model being a joint distribution of the motion parameter values, which is what we want, and the associated effects of performing those motions. And of course, if you anticipate or predict the effects that you want, the outcome of your manipulation task, what we can do then is we can use this joint distribution in order to identify the parameter values. That's the fundamental idea in CRAM. And while I've stated it here as a joint distribution, and this would be the way that, for example, the paper by McNamee and Wolpert, 2019 paper that I mentioned yesterday, which does a wonderful job in explaining these ideas of internal models, in particular from a motion control perspective. It's presented most often in a probabilistic framework. And that's what I've said here, it's a joint distribution. What I want you to understand here, though, in CRAM, at the moment, it doesn't represent it formally that way as a probability distribution, but nonetheless, it's exactly what it's trying to do. And instead, what it uses at the moment is it uses knowledge in order to identify or to represent or to implement this generative model. But that's an implementation issue rather than an issue of what exactly it is doing. And it is effectively sampling this joint distribution, this generative model. And so it provides then the basis for mapping from the desired outcomes of an action, which you know because you've identified what you want, you've identified the desired goal of your manipulation action. And what you need to know then are the motion parameter values, which are most likely to succeed in accomplishing that. And that's exactly what NOROB will give you. It's implemented in Prolog, and it is exposed then as a first order time interval logic knowledge base. One of the things I found particularly interesting and rather exciting when I was learning about this is that many of these logic expressions, which expressed in first order logic, are actually constructed on demand in real time when you want to find some information about, say, the sensory motor data in the environment or in the robot itself. Now, this is very interesting because effectively a logic expression is a symbolic representation, but sensory motor data is subsymbolic. And so here we have the mechanism, or one of the mechanisms by which CRAM accomplishes this hybridization, this ability to combine the symbolic and the subsymbolic, so that you can ask CRAM through the logic expression, please provide me with information about what? About subsymbolic data. And these are called computable predicates in CRAM, but effectively they're the mechanism by which you can access subsymbolic data through a symbolic interface. And that's very, very powerful. NOROB also provides all of the background common sense that Guyan mentioned in the opening video, and all of the intuitive physics knowledge that you need. You need to know a lot about the world, your ecological niche of the robot as it's performing its task, in order to be able to fill in all the gaps that have been left when you've been asked to perform some underdetermined task. How to grasp the object depends on its weight, its softness, and other things. How should you hold it while you're moving it? Well, if it's a cup full of water, you better not hold it at some angle because you'll spill it. Same with a saucepan. And where should I get it? Well, so milk is a perishable item, so it's usually stored in a refrigerator. So that type of information has to be made available so that when you say fetch the milk, you know you first have to go to the refrigerator. That's your location designator. You have to open the door, and then you have to look inside and you have to know what it looks like. There's your object designator. So all of this knowledge, some of it you can specify a priori. Some of it is derived from experience, you learn it. And some of it is the result of simulated execution of candidate actions using a high fidelity virtual reality physics engine simulator. And so this is one of the core aspects of NOROB, that it has a very, very powerful internal simulation system called the inner world. I'll show you that in just a second in the diagram. And again, I emphasize that all of this is accessible and represented in a manner which allows all of this to be reasoned about as needed. So there are 5 core elements in NOROB, and they're embedded in this multi-formalism reasoning shell, but you expose it through this unified logic-based language layer, and that's how you interact with it. Even though inside it's a little messier than that, or messier is the wrong word. It's more varied in terms of its representational formalisms. So inside the very core of this, of NOROP, is your ontology and your axiomatization. So the ontology organizes the knowledge, tells you how robots configured, it tells you how objects are configured, it tells you about the situational context. You're in a kitchen, or you might be in a shop, or you might be somewhere else. And it tells you about the different tasks that need to be performed and the different behaviors. And then the axioms identify the roles that objects play. For example, a mug is a cylindrical vessel. It's got a handle, and it can be used to contain things. So the concept of containment. So this is a key aspect of the knowledge-oriented, knowledge-based approach, that you organize your knowledge and then you axiomatize it so that you understand how you can reason about it. We have a generalized symbolic knowledge base as well. Now, this is a way of representing knowledge which has been abstracted from experience, and particularly from an entity called NEAM. And NEAM stands for a narrative-enabled episodic memory, and it's learned with the WECA machine learning framework. So what's a NEAM? So a NEAM is, as I said, it's a narrative-enabled episodic memory. Now, just pause for a moment, because remember, in the last couple of days, we've been talking about episodic memory as being a pivotal aspect of long-term memory. We also talked about procedural memory. And so a NEAM, in a sense, is an interesting thing. And, oh, sorry, I beg your pardon, I forgot to say, we also talked about semantic memory. Semantic memory talks about general things, and it's also linguistic. So NEAMs in CRAM are a way of recording the object's experiences exactly as we understand episodes to be, the percepts, the poses, the control signals, everything it did, as well as, and this is crucial, a narrative description in symbolic form of what these things were, of the actions, the motions, the effects on the robot, but in a language grounded manner. So a symbolic narrative description of what these sub-symbolic experiences are. So again, a NEAM is another way of doing the symbolic sub-symbolic integration. Here's a pictorial representation of that. So we have all of the sensory motor data associated with some, in this particular case, some action being carried out in the virtual reality environment, and then the narrative annotation of that. So a NEAM, I want you to understand, is a way of representing your experience, sub-symbolic information, and a narrative describing what that is. Now, it's crucial that also you realize that in the episodic memories in CRAM, they also encapsulate some procedural knowledge, because it not only do you have the declarative knowledge in the narrative, but you also have information about what you were doing as you were experiencing these things. So in a sense, the episodic memory knowledge base, these NEAMs and CRAM, are a joint representation in a sense of your episodic memory or your episodic knowledge and your procedural knowledge. Procedural in the sense of motor knowledge rather than procedural in the sense of the way SOAR uses it. And it provides the basis then for all of the queries that you were going to have to ask in order to resolve the designators that I mentioned in the generalized action plan. You want to know what actions were performed by the robot, when they were performed, how it was performed, so that you can learn from them, so that you can repeat them. And now we come to the other element of NOROP, which is the inner world knowledge base. So this is a geometric reasoning system which uses a very, very high quality VR system, the Unreal Engine, and a physics engine as well, so that you can effectively, act out the manipulation task in a virtual world in a photorealistic way and in a physics realistic way to establish whether or not the values of those motion parameters that you have decided you want to try would be successful. And then you can decide on and choose between different options. So in other words, you act out before committing to doing the action, you act it out in a way which is really faithful to the way that it would happen if you did it in the real world. And that's one of the key focuses of the CRAM approach. In exactly the same way as, in a sense, we saw with Isaac as well. So you simulate the outcomes of your candidate actions, and then you establish the feasibility of them. We also attach symbolic names, and that allows us to infer background knowledge. So, for example, where an object is stored. So the knowledge base, this inner world knowledge base, has two roles in CRAM. One, it represents the belief state of the robot about itself and its world. So it's a way of representing, so it's the robot's view of where it is and what it's doing. And that also is, as I've just described, a way of reasoning about the possible outcome of your candidate actions, and then depending on the different options, choosing the one that's most likely to succeed when you do carry it out. And therefore two types of knowledge: current beliefs and then your projected internal simulation of future events. So these dual roles are fulfilled by the inner world internal simulation engine. But if you're acting in the world, in a virtual world, trying things out, let's say it's CRAM's imagination, you can learn from that. In the same way that we know that people can learn from practicing in their head, not just mental operations to do with knowledge and say arithmetic or imagining how they would do things, but they also can imagine physical activities. And there have been experiments that have been done which we know that people can improve skills by practicing in your head, even though you're not committing it to your muscular execution. And so the inner world also provides, in a similar way, a way of learning about the world, because if the world is a faithful representation of the world in which the robot is embedded, then you can learn about that world by simulating your actions in the world. And those generate, effectively, memes. And those memes then get stored in the meme hub, the episodic memory that I mentioned. Now, the virtual knowledge base, we're almost there. We're almost finished with NOROB. The virtual knowledge base provides these things that I mentioned earlier on, these idea of a computable predicate. So they're a way of saying, tell me something about the subsymbolic data in the real world, but present it to me, please, in a manner which is represented symbolically so that I can reason about it. And the virtual knowledge base is the mechanism which provides that functionality in CRAM. So it makes queries appear to users as if they were working with the symbolic knowledge base. That's important because the plan executive is indeed a symbolic system. It does another, or fulfills another extremely important task as well. And this is going to be very important towards the end of my walkthrough of CRAM later on when I talk about metacognition. The virtual knowledge base also provides a plan executive view. Now, view here, I mean in the technical sense, like we talk about views in relational databases. Effectively, they are an encapsulation of the current state from a particular perspective, from a particular view at an instant of time. So they are, as I've written here, a dynamically instantiated representation of what? Wait for it. Of the CRAM plan language interpreter. So in other words, over here in the virtual knowledge base, I have a logical view of what the interpreter is. But it's here in NOROB, and NOROB is a reasoner. And that means that NOROB can be used by the plan executive, which is hidden underneath this, to reason about the plan executive. Just pause and take that in. We have a plan executive which can reason about itself because there is a view of that plan executive over here in the virtual knowledge base and accessible to all the reasoning mechanisms of CRAM. So it can reason about itself. I'll come back to that again a little bit more when I talk about metacognition. Finally, something that I've obviously said implicitly as I've gone along, the whole point is that NOROB is effectively presenting all of this knowledge to the world as a symbolic knowledge base, even though it uses symbolic and sub-symbolic representation through the computational predicates and through the NEAM data representations as well, and the way that they combine the symbolic and the sub-symbolic. So effectively, it means that NOROB is treated by the plan executive as a symbolic object-oriented query system, a form of oracle. When you need to know something, you present your query in a logical or a logic-based formalism. You submit that query and you get the knowledge that you need back. And it's generated for you by NOROB. And in particular, what it's doing is it's going to be generating these motion plan parameter values that you need in order to execute the motions. Down here, I'll come back to this later on, and this little asterisk is important because not only can we view this as a resource, an oracle for the plan executive, but anyone else can use it as well. And I'll talk towards the end about this idea of open ease. So you can access, I can access, anyone can access around the world, can access all of the information in NOROB, all of what's been learned and encapsulated about the environments in which the CRAM robots work, and they can use them in their own labs. So I'll say a little bit more about open ease towards the end. So I just wanted to leave with the idea that this is an extraordinarily powerful knowledge engineering resource for robotics, which is pivotal in the execution of CRAM generalized action plans and is used as an oracle or a Siri for robots, as Michael puts it, in order to carry out these generalized action plans. But it is also a resource for other research laboratories. So this is what I was saying, this query and response. So when you're executing a task, there's an ongoing dialogue between the plan executive and NOROB saying, okay, I have an underdetermined query. I need to resolve my designators. Please provide me with the information I need to resolve them. And this is all of the information you need for your object designators, your motion designators, and your location designators. And NOROB provides that back to the plan executive. That query and response approach is equally useful when you want to do metacognition. Almost there in terms of my tour of the structure of CRAM. We have the action executive then. So GISCARD is the subsystem which does this adaptive parameterized trajectory generation, and it gets as input the motion plan that I showed you in the early slide where we had the Flanagan model. So with the parameter values that you have derived in this process of contextualization with the aid of NOROB. And we've got the perception executive. You've seen that working in the videos already. So it's the perception system which is providing the visual information which is necessary in order for the robot to act adaptively in the world in real time. Cogito then, the final module in CRAM, is the module concerned with metacognition. So metacognition, as we saw yesterday, is all about thinking about thinking. And so metacognition is the idea of maybe having a set of processes which can improve the way that you're thinking, either by generalizing or by specializing. And it uses a technique called a PEAM, a pragmatic everyday action manifold. It's an interesting term, but it comes down to a very simple thing. In the space of all possible actions and all possible outcomes, that space is huge, intractably large if you want to navigate. And so what we do is we identify subspaces within that, and these are called manifolds. And so you constrain your working to subspaces of all of these possible actions such that you're likely to be successful. And you don't have to worry about the intractability of that space when you're searching it. You can find yourself through specialization using this concept of a PEAM. Plan generalization then is a way of taking an existing plan and making it more general, perhaps by performing your actions in a different way, or by concatenating actions, or by showing how different actions can be extended to deal with, or an existing one can deal with other objects as well. And this is all affected with transformational learning and transformational planning in a formal sense. So that's what a team is. It's a subset of this high dimensional space of these motion parameter values, which are sufficient. So you don't have to look at everything. You can constrain your search to the ones that are most likely to work. Okay, so now I'm going to pause for a moment and take some questions. And what I'm going to do then is I'm going to walk you through the execution of a generalized action plan, remembering this little picture that I have you up here. This is what the generalized action plan has been translated into these elementary motion designators, and NoRob is going to provide me with the values of these parameters here for each of them, and the parameter values are the values which are going to maximize the likelihood of, when I pass this over to GISCAR to execute, that the action will actually be successful. So that's where we're going. Let me pause and see if there are any questions before I get into the walkthrough.
Okay, a reminder to participants, same as yesterday, if you have a question. Okay, perfect. Already we have from Julia. So
yes.
You can unmute yourself.
Yes,
Perfect.
thanks. Thank you, Anna. Thanks, David. This was very interesting. I have a couple of questions about the dimensions of this knowledge base you are referring to. For example, I mean, if I understand well, these names you are mentioning refers to the kind of something like recording what is going on during an action. If
Yes.
I understood it well. And
exactly.
I wonder, I mean, no actions is equal to itself, in a real world. And how do you summarize the I mean, how do you avoid that these names becomes, intractable in terms of numbers of names? If I grasp an object twice, the names will be different.
That's right.
Yeah.
And you're absolutely right. I mean, every time you can't do the same thing twice.
Yeah.
Because circumstances change.
Yeah.
So, but think of it as an experience. So this is data.
Yeah.
You know? So it hasn't been abstracted yet. So the names, and they're stored in a thing called the name hub, is a way of gathering a very large amount of data about how people act in the world. And names are generated in a variety of ways, in 4 ways. In fact, they're generated by the robot as it acts in the world, and they're recorded. So John Laird mentioned this idea when he talked about episodic memory yesterday. He talked about a trace of what SOAR did as it was reasoning about when it was accomplishing. It's the same thing. So a name in that sense is a trace of what happened as the robot was doing something. It's data.
So, but there must be some kind of pruning.
Oh yes, absolutely. And so, but just to finish that, so there's a robot as it's working in the real world. There's a robot as it's acting in a virtual world. We also have people doing it as well. So we're connecting names from people in a lab, lots of different sensory motor data, and also people working in a virtual world. So all of this data is being collected from 4 different approaches. Okay, but it's raw.
Okay.
And I think what you're pointing out is raw data like that is not inherently useful in that state, right?
Yeah.
So what you have to do, you have to abstract what's essential from it in some sense. So, and that's what is the point of the generalized symbolic knowledge base. And I mentioned that there was a machine learning package associated with this.
Okay.
So effectively, you're using a machine learning methodology in order to abstract what's necessary and then represent that information symbolically, so that it is available over here. So you're picking up on this. So the names are not directly usable, but they're an indispensable source of information, which can then be transformed, abstracted, and made available through this logic interface, so that it can be support the ontology here and then used in a query to answer the.
Okay,
So in a
okay.
sense that if you've got names of people picking things up, you might have 7, 8, 9, 10, 100 instances of it.
Yeah, that's
Your
yeah.
machine learning algorithm here will allow you to encapsulate that, and then that forms the basis of your generative model.
Okay.
You sample that generative model, you identify the one which is most likely to succeed. How? Because you internally simulate it. You identify the best one, and then you hand that back
Okay.
over here as a response.
Okay.
Does that make sense?
So this is So this is not you know a database with the size which increases as long as as you do experience your actions.
I don't know how big it is in
Yeah.
terms of size, and I don't even, to be honest with you, I actually don't know even how many episodes there are in it.
But all of them are.
But we're not talking about trillions.
Okay, but all of them are saved there.
Yes.
Okay.
All of them are saved and accessible in the NEAM Hub.
Okay.
And one of the big successes over the
So
past.
this is, how do you reconcile this with the fact that we don't really have this powerful ability to remembering, all individual grasping actions that we performed in our life?
No, we don't. And as I mentioned yesterday, episodic memory is constructive. So when you remember, how did I make a cup of tea before I came in order to give this talk?
Okay.
I mean, my recollection of it is reconstructed. I don't have a trace.
Okay.
As a human being of everything I did.
But the system has the names.
But the names provide the data, which allow me to learn.
Okay.
This. Yeah. They also, if you have a specific thing, I understand what you're saying is you can actually query a name through this NoRob and say, okay, well, but this is part of the learning experience, because one of the things that I understand people are doing is they're saying, okay, I want to learn how to grasp I don't know, cylindrical objects. So they can query the NEAM database over here and say, okay, give me all instances of occasions where people or agents have grasped cylindrical objects, and then I will mine that so that I can learn from that about how I should grasp.
Okay, thanks. Now, I have another one, but I'll keep it for the end because maybe others other people want to ask questions.
Or they may be just relieved.
No, we actually have 2 others that are waiting.
Oh, okay.
So, Alessandra, if you go, and then there's also Levi.
Yeah, thank you, Anna, and thank you, David, for the presentation. It has been quite interesting. My question actually follows up on Julia's question on names. And also on something you said, which you eventually will speak again, but you said that we could use the NoRob for other applications, let's say, so to get a query of an action, let's say. But in this particular case, so if I try to apply a NoRob to a different robot, there won't be, let's say it's a new robot, it's starting to operate in the world, there won't be any new name for this action. Correct? Because there is no previous experience.
Not for that particular robot, but it's the same thing. I mean, the names are representing information for people doing it as well, different people doing the same thing. So doing pick and place exercises. I think am I right in what you're driving at is that how is that then going to be made available and then useful by a robot with a different kinematic configuration and a different dynamics, right?
Exactly. Because it doesn't sound to me that it's particularly useful if it has a completely different structure. Yeah,
okay. Yeah, but don't forget that in the ontology and axiomatization here in NoRob, it has all of the knowledge of the particular robots that we're working with. So whether it's universal robots or a PR2, and that information is there. But so the information that you're abstracting from this is the information at a level of representation which isn't specific to the kinematics. I mean, if you think about it, and the way I understand it, okay, and I'm open to being correction by any of the team, the CRAM team, which are sitting in on this, but for me, the key thing is in robotics is you have to identify an appropriate level of abstraction. in which to represent tasks and actions. And for us in CRAM, we've chosen the level of these elemental motion plans and these motion designators and their parameters that are associated with them. And they're not agent specific, and they're not robot specific. So if you think about it in ROS or YARP or whatever you're using, if you want to pick up and manipulate an object, what you need to know are effectively represented using poses. I mean, that's what we do in robotics more than anything, is we represent objects as using homogeneous transformations or using quaternions or whatever is your formalisms, but you're representing poses and you're representing grasp positions, but everything comes down to that computational geometry. So as long as you're representing the objects that you're manipulating using those poses, you need other things, of course, because you'll need things like grip forces. You'll need to know something about the friction of the object, and that's contained in the information in the object designator. So you know that if it's a very slippy object, you'll have to apply a higher gripping force, a normal force. Okay. But all of this is inherently accessible. It's effectively it's an example of robot functionalism. And so you learn the information from this agents, which are obviously specific instances of agents, but what you're learning is abstracted information at that higher level of abstraction, which can then be deployed. You know about the kinematics over here, but also Giscard, which is our action executive, it also, it obviously has to have the inverse kinematics of every robot that it's using. Otherwise it can't work, right? But the point is that the information it's being presented with are effectively these motion these motion elements with each motion parameter value, and then it interprets those. And when you do inverse kinematics in robotics, what you do is you just provide the pose specifications, and it determines the joint values and the Jacobians that you need in order to carry that out effectively. That's what's happening down here. Does that help answer it?
Yeah, definitely. Thank you.
Okay.
We have Levi next, and then there's also Fulvia that had a question.
Okay, so again, thank you very much. This has been really great. So my question is about the metacognition, and I'm not sure if it's a well-posed question, but can the views of the metacognition be associated with the NEM?
I don't see why it would be. I am going to talk about the metacognition in a bit more detail in a moment. Okay. I'm going to do my walkthrough, and then I'm going to take 10 minutes to walk you through the rather unique way that CRAM views metacognition, because I viewed, if you look at this diagram up here, I've got a module, a whole module called Cogito, with introspection and self-programming, and it's sitting out there, and it's the way that other architectures do it, the way that Isaac does it. But in fact, I've got a little surprise for you, which is a kind of a very, very elegant wrapping around on itself. But I'll explain that in a while. Okay. I don't understand, was it Levi?
Yes.
But about why I would want a NEM in the metacognition. Let me just think
So I'm not sure if I made a mistake in my question, but what I meant is we talked about the views so that we could self-reason about our state and what we were thinking. And so if you can associate that with your NEM, which is my understanding is what happened at the time, you could associate what you were thinking with what you were doing in a higher level sense than what motor commands you had and what actions or what you saw as a result.
Yeah, I understand. So this relates back to Julio's point, is that the NEM database here is encapsulated in a generalized way in NoRob and then made available for your metacognition. So you're not accessing necessarily the data directly. Mm-hmm. You've abstracted what's useful about it. You've generalized it, and it's that. So when you're thinking about thinking, I mean, when you're doing your metacognition, you raise a good point, and I'm not sure I can answer it, whether you would be thinking about the process by which you had done it, or whether you would be thinking about a specific instance and trying to generalize from that particular instance. So do you generalize my understanding is that you generalize an already general action plan rather than trying to do inductive reasoning based on a particular instance. I think that's maybe what you're interested, what you're doing. So very often you do inductive reasoning on multiple instances and then identify a pattern to say, okay, so now I can generalize that. That's how I'll approach all of my approaches in this circumstance in the future. I think that's what you're driving at. And
yes, and that answered my question, I think. So
okay,
thank you very much.
And it's doing a slightly different thing over here. It's actually reasoning about the plans itself.
Okay.
Right. But it's I'll check back. But that's a really interesting point about metacognition being an inductive reasoning about a particular set of instances of an action in order to identify the plan. So that would be, in a sense, that's about plan construction inductively by observing. Yep. As opposed to what I'll be talking about is reasoning about the plans you have in order to make them more effective through generalization or specialization. Yeah, it's an interesting point. Was there one more?
So we have Fulvia, and then there's also Antonio.
Okay, so thank you, David, for that insightful description of the framework. Unfortunately, I couldn't be here yesterday and the day before yesterday, so maybe hopefully my question is not too naive. So I think that the relevant thing is, of course, as always, the interplay between the symbolic layer and the motion numerical layer, no, which is quite ambiguous in general. No, it's as a matter of fact at the core level of what cognition is. So in fact, I mean, my question is related exactly to this. So there are certain approaches that are now labeled something like task motion planning, where people are trying to devise mechanisms to plan activities that in a sense borrow or take into account maybe the motion planning, and at the same time how certain motion planning constraints that you may have may constrain, on the other hand, the kind of sequence of actions that a robot could be able to perform. So instead of going top-down, like sequence of action may be parameterized or contextualized, you also take into account directly from the beginning the constraints that you have in motion. I was wondering, I mean, what's your thought on that? And if in any case, could a good way to go, or in a sense, it has some limitations?
Oh, okay. Yeah, if I understand you correctly, your point is that the way that you can act in the world provides constraints in the way that you can think about how you do things.
Yeah, yeah.
And so you shouldn't attempt to reason in a constraint-free manner and then find that it's not realizable in any useful sense when you actually try and commit to it.
Sort of, yes.
Yeah, okay. Oh, but another way of saying it is that you would want to be able to access how Giscard, the action executive, is actually carrying out actions so that you can incorporate that in your reasoning. I don't know if we can do that yet. Michael is there, and he may wish to interject and explain that. But at the moment, Giscard provides this adaptive execution of these motion plans. It's given a kind of a template saying this is the way we think you should do it, but it's free to carry out that in a different way using. It won't always take the same trajectory that has been suggested. So it's more adaptive than that. And in the next phase of Giscard, what we'll be doing is we'll be doing real-time prospection so that you are doing error correction as you're doing, so effectively predictive control. So that's the next stage, which is like visual servoing. I mean, that's crucial. Like, so we don't formulate a plan, close horizon, and hope it works. It won't. So even adaptively. So we need to make that based on kind of a predictive control. So that's in the works. That's not quite, I think, what you're driving at. You would like to be able to use that knowledge here in order to be able to constrain the plan that you've provided it in the first place, to close the loop, if you will, at that higher level. And I think that's an interesting idea. I can see a double, I don't know what's coming up back here in this arrow into the motion thing. So I just don't know.
Well, in particular, just as a small follow-up, I was referring to such, I mean, there are quite similar formalisms like PDDL plus, which are in a sense based on the same kind of Lisp-related formalisms that are used here, that could also embed some sort of numerical reasoning within the planning process. No? Yeah. Of course, they have some limitations, but I think it's a nice way to go. Although some numerical reasoning, I guess it's already part of this architecture. So
yeah, it is. Okay, but yeah, my depth of knowledge isn't sufficient to be able to really deal with that question in a satisfactory manner. So I'm going to kick that one to touch.
Yeah, thank you.
But thanks for the question. It's given me homework, which is good.
It wasn't my intention.
No, it's a good thing. It's a good thing. Thank you.
I think we can take also Antonia's question, and then maybe we can continue with the second part.
Okay, a very quick question, which is related to Giulio's question. So do you have a mechanism in NIM for forgetting? Because as Giulio was mentioning, you cannot store, I mean, it doesn't have any kind of plausibility to store all the possible, let's say, sequence of action that you have. So you should have a mechanism probably of forgetting, which can be based on some metadata that you go and to associate to these elements that you store in your episodic memory, such as frequency, recency, and so on and so forth. So in such a way, you can reduce let's say the size of these episodic memory and make the knowledge that is there more usable.
Okay, so to the best of my knowledge, that's not the focus of the NIMs in this episodic memory here. It is, as I said, it's a resource for learning so that you can generate this generalized symbolic knowledge from this data, which allows you to populate your generative model and therefore provide the information which is required to resolve the action designators. In phrasing my answer like that, it is an explicit admission that this episodic memory here is not an episodic memory in the way that we understand it in cognitive science and in the way that I explained it yesterday. And in the way that people like Schachter and Addis and all of these people doing episodic future thinking conceive of episodic memory. That's something which is more constructive, and it is something which is being planned in the next phase of the EASE project. So EASE is the project which is effectively funding the development of this work at the moment. And it's being planned in the context of this situation model framework that Werner Schneider and Helge Ritter and Josefina and Xiaoxia Xuan have been developing. And they have explicitly founded this on episodic memory in the cognitive science sense, that you understand it, and that Schachter and Addis and all of the rest of and Spunar and people. And also on the concept of working memory in the sense that Badley introduced it and developed it over many, many years. And so in order to have CRAM be a realization of that more cognitive science-centric view of things, then it will have to have a different perspective on what constitutes an episodic memory here, in the sense that it will have to be constructive. It will have to do consolidation. It's already doing consolidation here anyway in the symbolic generalization. But it also will have to address the important issue of the finite capacity of memory, and also the fact that forgetting happens for a number of different reasons, because of interference, and because things get overwritten. And so when you start to factor those things in, you generate a much more cognitively science plausible model of what episodic memory is. That's not what this is. Right?
Okay.
And so I don't want to mislead it. So, and it's not pretending to be either.
Mm-hmm. Okay.
I mean, in a sense, it's a resource for learning what matters as agents act in the world, rather than being a faithful model of episodic memory or procedural memory, in the sense of cognitive science, and in the sense that we would have to address it if we want to implement what are called behavioral episodes in the situation model framework. And these behavioral episodes are effectively sensory motor contingencies drawn from episodic memory and procedural memory in that strict sense. But that's not what this is attempting to do. That's not been its goal. It's been a way of abstracting and learning from demonstration in the world implicitly by abstracting general knowledge. That's my understanding of it.
Okay.
So,
thank you.
Does that help clarify that at all, Antonio?
Yeah. Sure.
Yeah. Okay. Good though. And it's very important that's a hugely important question. And let me just cover myself here by saying I am attaching a confidence factor of 0.875 to my answer. So there's quite a large element of probability that I'm not being entirely faithful to that. But that's my understanding of how it works. If anyone from the CRAM team wants to jump in and contradict me, please do. But that's my understanding. And I do know for a fact the next phase of these is going to be addressing exactly that situation model framework with behavioral episodes, borrowing faithfully from Badley's work on, and others, who's the other one, Fuster's work on working memory, and episodic memory as it's understood in that sense, with all of the entailments for forgetting. Okay.
Thanks.
Okay, great question. Thanks, Antonio.
Thank you. I think it raised a very interesting point maybe for the end discussion on how forgetting works in terms of episodic memory. Okay,
Yeah.
I think we can continue with the rest.
In case I forget, by the way, one of the best papers, I mean, I've read a number of papers, but there's a very good paper on memory, both natural and artificial in the context of cognitive robotics, written by a group of people. I can't remember the name of the project, but I think the lead author was Paul Baxter. It's a terrific resource if you just want this wonderful overview, including the issues of forgetting. And then there's another paper I have in my book on specifically on forgetting, but it's crucially important. Because in a way it says it's a prioritization issue as well. It's not just an interference issue. It's also a prioritization because you remember what's important. So I guess it's also related to the issue of attention, which isn't something I've mentioned here, by the way. Anyone who's if you'll forgive the pun, paying attention will notice I've not mentioned attention yet, which is an interesting omission. Okay, moving on. Where am I? Where have I gone to? I've gone to here. Okay, so the next phase of this afternoon is to walk you through the execution of the Generalized Action Plan, to try and bring some life to these modules and components that I've talked about, remembering that what we're trying to do is we're trying to map from a Generalized Action Plan, which is a way of encapsulating a vague, underdetermined action description like, get me a spoon, and mapping that into this motion plan. There's a motion plan over here in orange, and in particular identifying the motion parameter values which will make that action successful. And it's a three-step refinement process. It's called contextualization, and I now want to, explain what I mean by that. So it starts like this. Remember, we have a generalized action plan for each action category, like fetch, like cut, like pour, like place, or the the kind of concatenated one fetch and place. So that's where we start. We've got a generalized action plan. Now these are predefined, right? We've written them. Or more specifically, Gajoyan has written them. And so the next thing you need to do is you need to invoke that plan, say fetch a cup, place it on the table. So you select your generalized action plan. So here we have it. There's the generalized action plan for that particular class of underdetermined action description. And if you want to, there's a nice little video, the spoon challenge. There's a YouTube showing you exactly this happening. So this is the generalized plan, which has been instantiated. So the next thing then is it needs to interpret that generalized action plan. And that uses a process called contextualization. There are 3 steps in it. So the first step is to take your selected generalized action plan, instantiated. Here I want to fetch and place an object. The arguments in the generalized action plan are your designators. That's the key thing. These are the kind of the jewel. We have a generalized action plan, and the jewel of this in the formal sense are the designators, which are the constituent components of it. And those designators can be actions, high-level actions, which get resolved into motions eventually, but also objects and locations, because you're acting on objects at locations. The second thing, once you've instantiated that, you say, okay, so I'm now going to extend it, and I'm going to add all of the parameters which I need in order to execute the motion plan. Now, the way I've presented it here, it's kind of an atomic extension. So if you will, there's a grammar of these generalized action plans, so I know what the constituent motions will be in it. And so therefore, if I know what they are because of the grammar, I know what the motion parameters are. So in here, if I want to perform an action, it's of type fetching, I can populate this by extending it with all of the arguments, the parameters here that I know I'm going to need in order to resolve that. So here, I need to execute, I need an object, need to know what arm I'm going to use, I need to know what grasp to use, I need to know what lift pose in order to fetch that. I don't know any of this yet, right? So this is a mechanical process. So this is my second part of contextualization. I'm extending my generalized action plan on the basis of my knowledge of how my grammar effectively of the generalized action plan. So I know what my required motion parameters are. And then the third part is to query or to create a query for the values of those parameters. And I want the values that will produce some body motion which will achieve this action. And I can call it an underdetermined action description, or I can call it an instantiated extended generalized action plan. And I need this information. Everything in red over here I need. And so I query for that, and that query then forms a query. So there's my query for all of these things. I need my fetch location, where the robot should be when it's fetching it, and give me the information about the arm, the object, and the lift pose. So that query then is sent to NoRob. Effectively sampling this joint distribution of parameter values.
David, there are some issues with your audio.
Batteries probably.
Okay.
Can you hear me again?
Yeah,
I switched
yes.
microphone.
Yes, that's perfect.
Okay, I'm not sure which ones work. Can you say something, Anna? So I can...
Yeah, testing.
Oh, it's coming in on the AirPods thing. Anna, can you just interrupt me?
Yeah, no problem. I can keep talking.
Just, well, interrupt me if for some reason my audio stops, because my...
If it stops again, we will. In any case, now we hear you very well.
Great, sorry. Okay,
Right.
so this is what NoRob is doing. It's effectively using its generative model to find, sampling this space of motion parameter values, which is what you want, and the associated outcome, which is what you've told it you want. Okay, and rather than using some probabilistic graphical model in order to do that, it uses knowledge and reasoning. It could use a graphical model or some probabilistic formalism, but at the moment it doesn't. There are some plans in order to expand CRAM so that it can. And this ability to expand the formalisms is something which I'll talk about in about 10 minutes time, which is really important to how CRAM can provide a way of being extended or extending its capabilities. It is both, if I can put it this way, it is both robot agnostic as well as being formalism agnostic, in the sense that it's not tied to these things, and that's quite important. So as I said, it accomplishes that prospection using the inner world model. This is how it assesses whether or not these parameter values will be successful. And then it returns those parameter values back to the plan executive. And the plan executive then populates the motion plan that we showed you in that diagram with these parameter values and passes them over to the Giscard action executive, which then says, thank you very much for that. I will then execute that action adaptively and by creating adaptive trajectories as it, with its knowledge of the inverse kinematics and the dynamics of the robot for which CRAM has currently been configured. Okay, so that's how it works. I'll just briefly run you through that again, so you get the idea. You've got a generalized action plan. You extend it. You identify the parameters associated with the motions that you know constitute that generalized action plan. You make a query for the parameters to NoRob. NoRob samples the generative model using knowledge and reasoning, checks to see whether or not if those will work when its internal simulation, passes the values back, and then they move on and are passed on to Giscard for execution. And it just carries on doing that for all of the individual actions that comprise a given task. And that's exactly how the video that I showed you at the beginning operates, in a cyclic way, going through all that for your generalized action plan. Okay, so now I can move on to talk briefly about, do you want me to pause? I think that was pretty self-explanatory, so I'll move on. So now we've got cogito, so the metacognition. So there's a surprise here. So the idea here is that, and this is an unusual idea, the idea that your cognitive architecture can be viewed as a form of interface layer. That is to say, an interface between these high-level, everything above this is all of the plans that you're formulating in order to accomplish, perform actions and accomplish tasks. And then underneath it are all the formalisms. So effectively, we view CRAM and the cognitive architecture as an interface, and it exposes a self-programmable generalized action plan interpreter. Remember, that's what the plan executive is. The plan executive is, which is an extension of Lisp, is an interpreter which can interpret plans which are written in Lisp, and they therefore can be reprogrammed, or it can program itself in order to generalize its plans or specialize them. And in the process of doing that, it will update other aspects of the cognitive architecture. So this gives you an extended generalized plan language. So you can, your language isn't static. Your CPL can be extended by reasoning on your plans and producing new plans. And of course, if you extend your language, you extend your interpreter. And that's how it encapsulated that here by effectively showing the enlarged version of the plan executive. So the plan executive is not fixed. It can self-program. The question is, if anyone has any sense, whenever they see the word self in front of something, they raise their eyebrows and go, explain to me how that circularity works. And so I'm going to. The knowledge bases are updated in order to accommodate that extended interpretation. And this interface here that I've drawn allows you this robotic functionalism that we can run CRAM using a PR2, using universal robots on a mobile base, using Boxy with KUKA arms, and it's been used with also with Pepper Robot. And one of the things I want to do over the next couple of months is use it for a very, very simple 5-degree freedom teaching robot. So it's, and that should be absolutely no problem because of this robotic functionalism, this agnosticism towards the type of robot you're interested in. But all of the implementation processes, all of the things you need to make this work, your Hadoop, your data science, your transformational learning, your deep neural networks. I haven't written in here graphical models or Bayesian networks, but there's no reason why you can't have those. So they lie, these are what lies underneath it. I mean, the best analogy I have for people who are interested or who have studied relational database systems is we view SQL. The SQL is an abstract interface to what we think are underpinning it, the components of a relational database, but they're not implemented that way. And when you do Cartesian joins, you're not doing it in any sense. The data structure underneath it are far more sophisticated. But we have a logical view of it, and that's what the role that CRAM is playing here. So how does CRAM implement metacognition? And it does it in a unique way. So it uses NoRob in order to do the inference mechanisms, and it can do that because I mentioned this earlier in the virtual knowledge base. The virtual knowledge base has this view, I think it was Levi was asking me about this view, which is a dynamically instantiated representation of the language interpreter itself. And so the point is that the virtual knowledge base, which is also axiomatized, and then provides a mechanism by which I can reason about the plan executive. Well, what's doing the reasoning? The reasoning is being done in NoRob on behalf of who? On behalf of the plan executive. So the plan executive can reason about itself using NoRob because NoRob's got this this view of the interpreter axiomatized in its virtual knowledge base. So in other words, what I have here isn't so much that I've got a separate module out here. So the plan executive effectively self-programs, and you can, and this is the important slide. So metacognition isn't so much a different module, although it's drawn logically like that, but it's actually a logical extension to the plan executive with reentrant processing. So in other words, the plan executive can invoke reasoning on itself through this virtual view of the plan executive, and then change the interpreter and expand the language and increase the capabilities of the plan executive interpreter. So that's the overall idea. So it's a very elegant idea, and that's how, and it's all because effectively we are using first order logic and effectively using Lisp here as the language in which the plan executive is implemented and in which the plans are implemented. So that's the metacognition side, and I hope that that's helped Levi a little bit with what we were talking about earlier on. So now next we have something I mentioned earlier on. I just want to reprise it. I mentioned earlier on we have this NoRob can be viewed as a logic-based language interface, and I'm just highlighting here in red other systems can use it through this OpenEase interface. So let me show you a video about OpenEase.
David, sorry, does the video have sound and you're not sharing, or it's a mute video?
Okay, let me pause. Sorry?
I was saying, does the video have audio with it?
It has audio. It has.
Okay, we are not getting it. It's only the image. I mean, also check the player itself is not.
Okay,
muted.
well, so far there was voiceover coming, but that was just music, so you haven't missed anything yet. And Guyan's voice was okay. Let me stop sharing and reshare with the.
Yep, go ahead.
I think that's probably the best way. Share computer sound. Share. Okay. While I have stopped sharing, I'm going to take the opportunity to change my microphone, actually. I'm going to turn my Bluetooth off.
Go ahead.
Sorry. You could call this, oops, defensive zooming. Okay, so let me try sharing this again, and hopefully you can.
Okay.
Okay. You hear it?
Definitely.
Okay.
Today, state-of-the-art robots can perform complex manipulation tasks, but only in specific contexts, for specific objects, under specific conditions. But how can robots master manipulation tasks in realistic and open situations? For a task description such as pour something from the pot, the robot will need to know that this means tilting the pot, that if it tilts the pot too much, that it will spill, and that the weight in the pot will change. But right now, robots do not have that kind of knowledge yet. So, how can we get this common sense and naive physics into robot control systems and make it work effectively without delaying the performance? For humans, this is rather simple. If they, for example, need to know how to prepare a pizza or fix a flat tire, they most likely use a search engine on the internet. And robots? They can use OpenEase instead. OpenEase is a leading-edge knowledge service for robots and humans. Using OpenEase, a robot can ask queries such as, where do I grasp the object in front of me? How do I hold it? Where should I place it? The robot knows when and where an action was performed, how it was performed, what effects the action had, how the agent moved when the action was performed, and what the robot believed when the action was executed. OpenEase gives answers in such a way that the robot can use it to execute the respective action successfully. It does not only answer the queries of robots, but it can also collect their experience knowledge, generalize it, and make it accessible to other robots. OpenEase is synonymous for open research. The system is accessible to every robot in any robotics lab all over the world. Welcome to OpenEase.
Okay, we're almost done. So I just want to finish off with, I think, an important point, which is not related specifically necessarily to CRAM, and rather to not leave these three talks without emphasizing the complexity of the endeavor that we're engaged in. This is a slide that I got from Gerhard Kreutzmer a few years ago, which emphasizes the fact that when you're building complex systems, you better be aware of the magnitude of the task that you're engaged in, because a cognitive architecture is not as we said yesterday, it's not just a top-level representation or view or schema of your system. It commits to formalisms and it commits to specific computational mechanisms to make it all work. And so far, when I'm in the course of the lectures that this talk is taken from, we've been talking mainly about the functional architecture, always remembering that you need to have a component architecture for each element of it and then runtime architecture on which it runs. So the next thing to do, having understood CRAM or any cognitive architecture, is then now to go on to these different lower levels of abstraction and to be able to study how you can program, for example, in CRAM, how you can program in the CRAM language. And if we were to carry on with this, that's the next logical step. And as you'll see in the course in cognitiverobotics.net, that's where we would go next if I was teaching this course. In terms of CRAM itself, I'll just remark that 90% of CRAM is written in Common Lisp, packaged using ASDF, utilizing ROS for everything. It uses Emacs Lisp. This is I asked Guyane about this a couple of years ago, and I said, this is a complicated diagram. She said, no, this is the simple version. But it gives you an idea of the underlying runtime environment in which CRAM is actually implemented. So it's got all of ROS. It's got a Steelbank Common Lisp compiler. Emacs is effectively the IDE that we use. And as is always the case in any robotics endeavor or software endeavor, you have to learn both the theory and the principles, but especially learning the tools. And becoming proficient in the tools, takes practice and takes time, like any skill. One way to get a feeling for what is involved is to do a tutorial. This is what's called the zero prerequisites demo tutorial. So it's a way of learning how to program CRAM. There's a virtual machine with CRAM pre-configured where you can download it and use it, and then you can try and do this tutorial. Last year, when I was teaching in CMU, I gave this as an exercise when I was teaching. One of my assignments I gave to the students, and they came back and they said, we're not so sure about this zero prerequisites bit, but it was really instructive. Or their point really was struggling to complete it was they found incredibly valuable in learning at a deeper level beyond what I had taught them, grounding them grounding what I had been teaching them in real experience. So you can do that. Or alternatively, you can watch Guyane Kasayan do it. So there's a nice tutorial, I think it's about an hour long, where she actually walks through it, if you wish. So that's the zero prerequisites tutorial. So you can either do it yourselves, or you can watch Guyane do it, or you can do both. So that's it. That brings me to the end. If you want to read more about CRAM, there are many, many papers, but the two I've just picked out here are the original, the original seminal paper by Michael in 2010, which got it all started, and then a more recent one, which is the next generation of NOROB, an overview from 2018 on how that developed in the intervening 8 years. And then Guyane's tutorial then on CRAM, which is available also on YouTube. So there we go. I'll stop and we can have more questions.
I will allow people also to unmute themselves if you want, considering that we have now a very selected list of participants.
Well, thanks, David. Thanks a lot. This was very interesting. I leave the floor to others if they want to ask.
Yeah. Well, I hope you have a better idea, Giulio, now of what's involved.
Yeah,
I mean,
yes. Yes.
There's a lot there.
Yes. Yes. I appreciate one of your last slide with synthesis that it is a complex system. Yeah. I agree with that. Yes. But it was very, very insightful.
Yeah, but then the brain's a complex system, and cognition is a complex process. So you can't expect it to be anyway for even the good old cybernetics, good regulator principle.
No, it's
no free lunch.
Yeah, exactly. Yeah.
We have a question from Alessandra, if you want to go ahead and ask.
Yeah, thank you. So first of all, thank you for presenting the system. I realize that given the complexity, it's really hard to put everything into a presentation, well, of 2 hours, but anyway, it's still complex. I have plenty of questions. I guess I'll have to search for some of the papers, but some of them maybe I can ask you now. So one of the things that I was interested about is at some point you were mentioning that, when you're selecting the motor action, there were some fields, for instance, corresponding to the pose of the object, correct?
Mm-hmm. Yeah, correct.
However, I didn't see this on the logical side, let's say. So the list actions, let's say, that you had on the logical side did not have a pose. They were very abstract in this sense.
Okay. Yeah. Yep. Sorry, I'll wait for your question.
Yeah. So my question is, so for instance, let's say that you instruct a robot to cut a piece of cake, for instance, and he has to use a fork because it only has a fork available. How does it know whether to grasp the fork for a scooping motion or to grasp the fork for a cutting motion? Given that, it's not present on the whole plan structure, at least from what I can tell.
Yeah. Okay. So it's a terrific question. And it goes back up to this idea of the generalized action plan. So let me just back up to that. So the idea here is that we know you're either doing scooping or you're doing cutting. So therefore you've chosen a particular generalized action plan for that category of action. And that generalized action plan has these designators in it. In this case, I was talking about fetching and placing, but it could have been cutting or pouring or something else like that. And as I said, then the next thing you do, that this gets extended. Where was it? Yeah, you get extended. So that generalized action plan for that category of things, would it be cutting or scooping? That gets extended into all of these, or resolved into all of these lower level designators. And some would be objects. There's an object designator. And so it's not obvious here, but in this object designator, when this is resolved, that's when you get back all the pose information you need for the object that you're fetching or manipulating, cutting or whatever. So that's how that gets resolved. So that's an object designator. So everything you need to know about the object in order to grasp it is contained here, right?
Okay. Yeah.
Okay. So that's where that's.
Okay. That was not the obvious part. Is that the object contained this kind of information?
Yeah.
On the generalized action plan.
It does. Okay. Exactly. And that object then. The argument for this, or the parameter value for that, is then provided as an argument, if you will, to the motion.
Yeah.
So it knows what the pose, the grasp pose is, the position pose, and all of those things. It's the same thing here, for example, with this construct with robot at location. What does that mean? Well, this produces actually a distribution of possible poses to which the robot should go in order to stand so that it is capable of doing this action.
Okay.
And then the grasp one down here will have force information associated. So, I can't remember if that's the force one or if that's also pose, the grasp pose. Yeah, and then this is selecting of which arm you should use. And all of these things sorry, I beg your pardon.
No, I was going to try and understand. So basically the motion plan is what integrates, let's say, the logic part with the actual representations on the real world and
yes. Exactly.
So exactly.
Yeah, it's in resolving these designators. So these designators are placeholders, and they need to be filled in with all of this detailed information, which are then passed and provide the arguments for the motion plan, which are then passed over here.
Okay, thank you.
Yeah. So the way I view it is, I learned robot programming from Paul's book, which is basically task-based or task level specification, and everything comes down to specifying poses. And gripping forces, and occasionally some dynamic stuff. But that's ultimately what you need. You need that low-level information. And these are the placeholders where they're provided. Through the extension of the generalized action plan, it gets expanded into this motion plan and then NOROB provides the parameter values, and it does so through knowledge and reasoning, given all of the knowledge it has about the world. Yep. So you would know how to grasp it because it was a cutting action. It would know that it would provide a particular pose for grabbing it as a cutter as opposed to as a something else.
Super. Yeah.
Yeah.
Okay.
Makes
Thank
sense?
you so much. I have a lot more questions, but I guess I'll let other people go first before hoarding all the time. Thank you so much.
You're welcome.
Antonio, you can go ahead.
Okay, thank you. I have a question about the common sense reasoning part that is going on in the architecture. So if I understood correctly, you have an ontology which is available, which is written in some standard language like OWL, something like that.
Yeah, that's right.
Okay. So this is what, let's say, strikes me a little bit, because in languages such as OWL and in general ontologies does not support, they do not support common sense reasoning. So they just support, let's say, logical deduction. So my question is, and also the reasoners that run on this kind of knowledge base support logical deduction. So do you use some kind of internal rules within your neural knowledge base in order to, let's say, try to extend this kind of reasoning, or how do you deal with this kind of situation? Because it is not native of the formal ontologies.
Yeah. Okay. So thanks, Antonio. So here's where I just say I can't answer that question. I don't have a deep enough understanding of exactly what's happening.
Can I step in?
Yeah. Oh, yeah. Please, Michael, do. Yeah.
Yes. So in general, so you have the OWL, which basically defines a terminology. Then you have heuristic rules that you can either hand code, but you can also learn generalized rules from experience or from observing people. So this is a way people typically cut a piece of bread or something like that. And we are supporting all forms of this kind of common sense knowledge.
Okay, yeah, this was the question. So are these rules encoded in, for example, some format like SWIR rules or RIF rules in the ontology, or do you use another language for encoding these learned or pre-programmed rules?
So some of them are basically explicitly coded as heuristic rules, and other ones can be learned classifiers. It can be a deep network or anything that basically can be called as a generalized inference tool, right?
Okay, thank you very much. It's very interesting because these open ease, let's say, approaches reminds me a lot of the many approaches coming, let's say, which are related to knowledge engineering and reasoning framework, where you try to attach these, let's say, word level knowledge to, for example, in this case, to a robotic agent. So another question which is related to the previous one, which was more on the reasoning part, is did you try to, let's say, attach these very specific knowledge, which, let's say, is the interface that you need in order to, let's say, connect the action plan and the motion issues with more with other ontologies which are available from the knowledge engineering community, like, for example, psych, or like, for example, other kinds of knowledge base, word level knowledge base which are available, because this would be a good connection and a very interesting one in order to allow this system to not play just with, let's say, this very specific and in some sense, let's say, also, narrow knowledge bases.
Yeah, so we were starting with psych originally, but psych was not strong enough in the physical action part. So now we are using essentially DAL, the upper ontology, very clean and basically go for specialized ontologies for different parts, and we try to get them standardized also with other researchers and also with some of the standardized forms of ontologies for autonomous robots. Yeah.
Okay. Thank you very much.
Thanks.
Thanks, Michael.
If anyone has more questions, you can feel free to unmute. So right now, in addition to Antonio and Alessandra, I don't see any other raised hands.
Well, I have just a curiosity. I mean, this I can't refrain from asking, because I like very much the idea of having an internal model of the environment, to an inner model, to reason about and to simulate and to somehow anticipate what is going to happen. I wonder, on the other hand, the way it is implemented with a very realistic environment, virtual environment. It seems to me that in this way you don't define the kind of resolution you need. I mean, it seems to me an overkill in some sense, or it seems to me that it does not capture the fact that let's say the resolution, the level of details of the world is very much dependent on the action also you have to perform. So in this case, it seems to me that you basically have chosen to put everything you can into the model, which again maybe is not very biological. It's not very biological somehow. So on some sense, I like the idea, and I think it is an important, a crucial part of the architecture. But I wonder if you think that this, I mean, there are other methods to do that, or this is basically the solution you think is the best one.
I can try that. Michael can pitch in as well. I don't think, I personally think it's a very pragmatic, engineering-oriented, wise choice. It makes a lot of sense, and it facilitates effectively the success of CRAM. It's certainly not biologically plausible. And we talked about yesterday, I remember this idea that some cognitive architectures have modules for internal simulation, and other architectures have effectively, they don't have a redundant mechanism. They simply have the cognitive mechanism without the motor execution, which is clearly more biologically plausible. And also that they use associative processes, heteroassociative processes between the different modalities in your sensory motor approach. So I'm looking forward to the next phase when we begin to dig deep into the situation model framework, and in particular try to implement, to see what will be required in terms of extension or not in CRAM. Yeah. If we want to implement a behavioral episode or a cognitive map comprising some network of behavioral episodes, because they view the internal simulation in a different way, which is effectively a much more constructive heteroassociative processing, whereby you do your inverse modeling by association rather than by execution in a virtual reality. So it may be the case that we need to augment these mechanisms if we want to realize the situation model framework. I don't know. I think it's going to be at a very, very interesting phase. But the one thing that makes me optimistic is this interface layer perspective that I showed you, that underneath all of this are the different formalisms, and CRAM is, as I said, it's agnostic about the underlying formalism. So I don't think it's going to be problematic to integrate new approaches. I'm not saying it's easy.
But
I think it's possible.
I fully agree with you that it is a very sensible engineering solution. I mean, it is, and I think that the important issue here is that you have to think about the whole system, even if you know that some part may not be the optimal choice, but they will be important to track the performance of the overall system. So in that,
and this is one of, sorry to interrupt you.
No, sure. You don't have just,
I think this is one of the huge strengths of CRAM, and that is the fact that it is a complete system. So it works. When you saw the opening video, it works. It may work slowly at times, but it works. And the magnitude of the effort that is required to put it all together, everything working in almost harmony in order to accomplish this is a major accomplishment.
No, it's a fantastic work, definitely, yes.
Yeah. But what's most impressive for me is actually, I mean, that in itself as an engineer is worthy of a huge amount of admiration. But the fact that there's actually a deep story underneath it, and that it is extensible, theoretically as well as practically, I think is actually, I think that's very interesting. So I think it's got an awful lot of potential. It doesn't have everything. I mean, but then I don't think we pretend that it does. But it is not complete, but it is in the cognitive sense, but it is complete in the system sense.
Exactly. Yeah. Oh, very nice.
And that's a big thing.
Thanks.
So maybe I can also give a little bit of my perspective. I think that having these detailed belief states is actually an opportunity we have because of modern game technologies, and they are basically acting in real time, acting in extreme detail, and anything we get in a scene graph data structure of a game engine, we also have as a symbolic knowledge base, as a virtual symbolic knowledge base. And that is kind of incredibly powerful in terms of reasoning and context-based reasoning. So if you basically do the same thing in a deep network architecture, I think it would be very difficult to get the same kinds of functionalities into a deep network architecture.
Yeah, thanks. Thanks, Michael. I agree with you. Yes, yes.
So maybe I can make another question now, if
sure,
if I'm allowed.
Great.
Okay.
Yeah.
Go ahead.
Go for it.
So this is one question which I was hoping to see in the examples, but maybe we can discuss it here a bit more. Because in the beginning of this presentation today, one of the points you made about this kind of cognitive architectures, in particular when addressing real-world scenarios, is that we should account for failure in some way, because it's going to happen. I wanted to know a bit more about how does CRAM react to unexpected situations or errors in the plan and so on.
Wow.
So, for instance, if the robot drops something, how does it stop the plan? Does it replan? Does it look for the object, etc., etc.?
Yeah, it's got a non-failure construct. So I could stop sharing and show you some examples from there's a pick and place tutorial. So if you want to do this, there's a tutorial both in my course online and also on the CRAM website, which in fact, they're mirroring one another, and the notes in mine walk you through incrementally a plan with no failure handling, a plan with a little failure handling, a plan with another different failure handling. So it incrementally adds on the failure handling to it, and it shows you how it does that. And then you can have multiple tries as well. So you can specify the number of retries you can have in trying to resolve a failure, and then some graceful degradation. The only way to answer that sense is to actually show you the code.
Okay. Yeah, that was going to be my question. So how does it, how does it perceive failure, first of all? So does it analyze the real world? In what sense? Is it symbolic perception? Does it check if an object corresponds to something? But yeah, okay. In this case, maybe I should check the papers and perhaps email the...
Well, actually, just have a look at the... I'll stop sharing. I'll share my... let's see, why don't I share my entire desktop? I can just give you a quick... so if I go to... okay, so there's some error handling here. So the last two ones have got some error handling. So error handling for looking in different places, and then error handling for, let's just go for the last one. Okay. So it walks you through the various things. Whereas it's been a while since I've looked at this. Okay, so effectively there's a retry mechanism, and then you've got your failure handling built in. So, but it's an additional code that you have to add in order to handle the different failure ones.
Okay.
So, so the tutorials, and you can either follow it from this, or you can follow it also from the. If I go back up here, there's a link to it. There's a link to the additional thing. So there's two ways you can do it. The way that the tutorial online does it, you incrementally add the code as it walks you through it. Yep. And you test the functionality as it fails, as you add the error handling and so on. Then I wrote an additional version here, which is on my wiki, which has got 3 versions of the plan with pre-coded into it, the additional one. So you can just execute one version of it or the next version of the next version. It's faster to complete. So I'm just alerting you to the fact that if you want to do that, if you've got the time to look at it, you can see the whole thing here.
I'll definitely check it, because the architecture seems very, very complete. As you said, like system complete, let's say. Yeah. So I'll definitely check it. Thank you.
Okay, so there you go. So on the wiki there, you can see all the different, it's a move bottle one with different error handling on it.
Okay.
Okay,
thank you so much.
You're welcome.
So there's Levi that wants to ask a question, and I'm not sure also if Yanis wanted. So I'm looking at also who has the arms raised.
Let's take this as a last question. I don't want to abuse, the endurance of David. I know he can give long talks, but he has been talking with us for more than 2 hours. So, but please go ahead, Levi. Maybe you can ask the last one.
Okay. Well, it was a simple question, but perhaps with a long answer. My question was, if you, if I were a company and I wanted to, make a robot to take care of mines, or I wanted to make a robot to sort strawberries, or clean up a house, examples slightly different than the kitchen scenario. Why should I pick CRAM? And what issues might I run into if I use CRAM? And I'm just looking for a general answer, not, all the specifics, but.
Yeah. Okay. So, if you want a robot system to do anything, you're after robustness, right? I mean, that's really the key thing. And the way that we can achieve that is we can restrict the environment and impose constraints, and that's the way we classically do it. So we reduce the scope of variability and improve our robustness that way. But what we're trying to achieve in cognitive robotics is we're trying not to resort to that particular strategy and be a little bit more open and adaptive, where we can, versatile, if you will. And a couple of years ago, we went through an exercise to try and find a cognitive architecture schema. So how would we build a cognitive architecture that would do all the things we wanted to do? And I was supposed to write a deliverable. He says, okay. And this was for industry, by the way. We went out to industry. We asked them what they wanted in a cognitive robot. We didn't ask academics. And there's a short paper, it's only 2 pages long, of the results we had from that canvas of industrialists and suppliers as well. So both end users and suppliers. And then we said, okay, well, if we want to build a cognitive robot that can provide that, what do we need to put in it? And we just failed to find and specify in a kind of a generic way that. And we resorted, I looked out and we said, well, what's the best example we have of a complete working system, which is extensible and which provides the potential for working in these different types of environments. And CRAM was the one that we came up with. And that's the one that we published in the report. So the reason I would choose it, so I always say to people, if it depends what you're interested in. If you're interested in a unified theory of cognition and understanding cognition and what it is, would I choose CRAM? And the answer is no, because that's not its goal. That's not what it's there for. It's there to build a robust system which is extensible and which is capable of working in real world environments which you don't heavily constrain. And that's, I think, its huge strength. It's not finished, but it's a long way from the start. So I don't know of a more powerful system, to be frank, which is this extensible and this well tested and is as complete as a system and works on multiple platforms as well. So from an engineering perspective, I think it's a tour de force. And I think from a computer science perspective, what I've learned over the last 4 months is it's extremely deep and far deeper than I realized when I wrote this report 3 years ago. I mean, my eyes have been opened over the last 4 months about the computer science depth to it, as opposed to just the pragmatic industrial engineering aspect to it. So it's got an awful lot going for it. I'm not trying to sell it. I don't have shares, and there is no company. But it's I mean, the thing that is most valuable to me in my life is time, and this is how I choose to invest my time in terms of cognitive architectures, because of the reasons that I've mentioned.
Thank you. That was a great answer.
Yeah.
Okay, so I think we can leave David to go back and make another cup of tea, maybe at this time. Time of the day, it's a right time. Well, I mean, I really look forward to collaborate with Michael Group's group and yourself on this iCog architecture, cognitive architecture initiative, and certainly not. I mean, there are aspects which do not resonate very much with what I think is important, but it is a fantastic example of a complete system, and as that it has to be. It is an important base, to start to work together. So with this.
I would give, just before officially closing, 2 quick notes. So for the people that are already actively participating in iCog, you can find also David in our group, and you can directly pester him there with more questions. I'm sure he will be delighted to answer after he probably takes several days to rest and recover from this. And for everyone that wanted just to join for the talk and would like to be kept up to date to all of our upcoming events, I shared again the links to our social platforms, and very soon we will also have a mailing list available to which you can subscribe, so that in case you're not a fan of Twitter or Facebook, you can receive all updates directly on your email. So those are my 2 very quick updates.
Okay, so the last word, if somebody wants to propose ideas and give a talk or discuss about a topic, just let us know. We already have Antonio Lieto scheduled for, sometimes
the 18th of February.
The 18th of February, and there are other possibilities either before or after that. We would like to really to be inclusive with ideas and groups everywhere.
Yeah, and I personally would very much like, what appeals to me personally from a kind of my own research philosophy, to follow up on Yanis's questions from yesterday. These were crucial questions, and they occupy a different space, a different dimension to the things I've been talking about today, and that's fine, you know. But we really need to be exploring the multiple dimensions of cognitive architectures. Today we've seen a very, very powerful approach, but it doesn't really speak to the dimension that Yanis was making, and I think I would be slow to lose sight of that. I think it's extraordinarily important to address those issues.
I agree. Okay. So, bye-bye. Go back and make ourselves a cup of tea. David.
Thank you very much, David.
Thanks a lot.
Well, you're very welcome. Thank you for having your patience, and thank you for sticking with it.
Thank you, David.
I'll send you the medals later.
Okay.
Antonio, congratulations on your book.
Yeah.
Thank you, Yannis.
You have a book on AI.
Yeah,
Very good, man.
Thank you.
I'm looking forward to reading it.
Yes.
Okay, that's
it's
great.
A nice book. Started reading it. Ciao. See you.
See you guys.
Bye.
Ciao.
Bye-bye.
Bye-bye, everyone.